When we defined electric flux, we defined it through an open surface. But we could have an example of a closed surface. For instance, a sphere here. This is an example of a closed surface. And how do I calculate electric flux on a closed surface? Well, for this surface, I can pick an area patch. Now, in this surface, I might choose some nice coordinate system, but for the moment, that's not crucial. I have an area patch on the surface, and now the question is, how do we choose the unit normal? So here, we have a little area patch. And for closed surfaces, we will always choose n hat to be an outward directed unit normal. We write it n hat. This points outward. Remember, any surface has two different directions. And for a closed surface, there's always a well-defined sense of what we mean by n hat out. And so for our closed surface, our area element, dA, we write as n hat out, and we multiply it by the area of the element. And so symbolically, when we want to write the flux through a closed surface, sometimes people will draw a circle here to indicate closed surface. We can put a little text here to indicate that it's a closed surface, and it's E dot n hat out times dA. And that's our definition for flux through a closed surface. Now, our first example, and by far the most important example, is a point charge. And so let's consider a point charge Q. And let's locate this at the origin. And I want to consider a sphere. So here is a sphere. And the sphere has radius r. And I would like to calculate the flux through this sphere. Well, I'll choose my dA, and I'll choose my unit normal out. Now, I'm going to choose a coordinate system in which the unit normal out is in the outward pointing radial direction. So r hat points away from the center. Now, here's where the physics comes into this calculation. We know that the electric field of a point charge is that constant kq. It goes like r squared, and it points in either the plus or minus r hat direction, depending on the sign of q. Here, let's just make q positive, and then I can draw my E field of the point charge pointing radially outward. And so now I can calculate this dot product. So my EQ dot n hat is equal, I'll write it down here, KQ over r squared r hat dot r hat. And r hat dot r hat is 1, so it's simply KQ over r squared. And now the flux, E, through our closed surface, this is a sphere of radius r, E dot n hat dA, and I'm writing that as a capital A. The dot product, first we compute the dot product. That's KQ over r squared, and we have a dA. And notice that on the surface of the sphere, r is a constant. And so there's nothing to integrate here. E is uniform in magnitude on the surface of the sphere. I can just pull it out of this integral. I get KQ over r squared integral dA. And now one has to remember that what are we doing when we're just adding up dAs? This is no longer a surface integral because it's not a dot product. It's simply calculating the area by adding up all the area patches, and that's kq over r squared. And by the way, lots of people forget what the area of a sphere is. It's simply 4 pi r squared, so we get 4 pi kq. And that's the simplest type of flux calculation. Now, k is independent of whatever units we choose, but when we're in SI units, remember k was 1 over 4 pi epsilon naught, and so the flux of a point charge through a sphere, the 1 over 4 pi's cancel, and we simply get q over epsilon naught. And that's our first and most important calculation for electric flux. It's equal, if we put a point charge at the origin, to the charge divided by our constant epsilon naught.